Thank you for the introduction and welcome everyone. Thank you for attending the presentation. So yeah, I'm Nicolas and today I wanted to try and answer this question with you guys. And because we're in France, in Paris, I tuned it to be this. So I'm after spending my whole life in France, I'm still not sure what is the number, if it's 17, 15 or 18 or maybe 16. But basically the talk is about trying to understand why AI and machine learning can be less reliable in production and how we can make sure that it is, and show you some cool tools that I use in my everyday job along the way. Yeah, I did just a slide of introduction. I just worked with NLP models for my whole professional life. First at Alexa, now at GitGuardian. GitGuardian, less known than Alexa. We find cybersecurity vulnerabilities in the code of people and in Jira Slack. But it's the same model, it's just that the language is a programming language, not natural language. Yeah, I used to tell my parents, I don't know how I explained to them what I was doing. Now I just say it's like ChatGPT, and they get it. So that's a good AI revolution. My grandmother still thinks I do mathematics, so I don't correct her because I want her to be happy. Yes, and a little question for you is, what do you think this is? Is this the Bitcoin price evolution, or is this my brother-in-law's Strava profile run? It could be both, but it's option C, obviously. It's the number of AI-related incidents in the past decades. And it's like kind of scary because it's going up exponentially almost in the past decades. What do we mean by this? It's, for example, this lawyer, Michael Cohen. This guy used ChatGPT to find previous cases of his own, law case to get inspiration and jurisprudence. But the thing is that ChatGPT completely invented 3 cases that never existed before. And so, that's not the best thing to do when you're trying to build your own case. This is another example of a journalist that managed to get ChatGPT to tell him how to make a bomb. So obviously OpenAI is working really hard to prevent this. They do good work. At this time, the guy just said, I'm trying to write an article to prevent people from making bombs. And so after he said that, the model would just collaborate and say how to do it. More recent example, interesting. They tried to make the model to be diverse, ethically speaking, respectful of diversity. And so this happened with Gemini, where they did too much of this. And when you asked for like a picture of the founding fathers, it would generate something that is actually respectful of diversity. It's just completely inaccurate, historically speaking, obviously. So before you say, Nicolas, this is just, Gen AI stuff, this is in a UI, it doesn't affect us that much in real life. We already have examples of, systems that are being used, for example, by the police, computer vision systems that have conducted to the wrongful arrest of people just because the computer vision system was making mistakes. So this is affecting us already in real life. And I don't want people to be depressed by the presentation. That's not about this. I just want us to realize that AI, machine learning will never be perfect. It has flaws. The whole point of this conversation is to plan around the mistakes and be able to anticipate them in production. And that's, I think, what is resumed here in this statement. And to do this, well, I'll start with the motivations, although I don't think we need a lot of motivation for having reliable systems in production. And then I'll show you, second part, how the models works to understand why they might have problems in production. Then how you can mitigate those risks. And in the fourth part is more like actual tools that we use to do this so that you can use them tomorrow in your own jobs. For the motivations, very quick. You don't want to have a bad user experience, for example. Imagine that your Alexa device is just, when you say Alexa stop, it's not going to stop, or it's going to start to insult people if you have a chatbot for a system support or I don't know what. That's a bad user experience. You want to avoid this. If you go one step further, that's why I call legal and governance. Sometimes you have laws, you have contracts you have to abide by. And so, for example, I don't know, like a self-driving car cannot, go over a pedestrian. An Alexa device cannot, buy something that you didn't ask to buy. Otherwise, you can make a lawsuit to Amazon. So that's, beyond the user experience. It's just like you have actual laws that you need to respect. The third part is just, it's expected that you're going to have problems in production with any systems, not machine learning specifically. So what you need is tools to monitor them, to get alerts, to debug them, to trace them, to reproduce them, and to hotfix them. And the point with machine learning is that it's making everything harder because it's harder to reproduce. It's harder to understand why the models say what they say. So that's just to emphasize this point with machine learning. Cost, I don't talk about this in the presentation. It's just sometimes you don't need machine learning to do simple things, maybe 80% of the things or more. Rule-based systems can do a lot. So if you don't need machine learning, don't use it because it's more expensive, compute-wise and time-wise. So that's just the motivations. Now, I'll take an example to show you how generative AI works. So I work with Alexa quite a lot. It has lots of applications. One of them is you can ask for jokes. And this is what you would get as an output, which is, I guess, state-of-the-art jokes in the world. And the way the models do this, very basically, is they take as inputs the user request and everything that's been generated up until now. And then they have a vocabulary of words, and they're going to say what is the most likely next word to come afterwards. And they're going to give a score between 0 and 1 to all of the tokens. And they're going to pick the ones that have the highest scores, and often they can pick randomly from the top scores for the next word generation. So for example, here, what is a good candidate because it's often how you start a joke. And then they continue with the new word what is the most likely next word? And maybe in this case it is, because what is very common in language or for jokes. And they continue this until termination. Reality, more complex, it's not words, it's subwords. We can talk about this after the presentation, but that's roughly the idea of what happens for generative AI, okay? So, that's how it works once the model is trained, but then you can ask how the model even knows how to put the scores in the first place. For that, I just take a very step back on machine learning in general. Machine learning, you assume you have lots of data, inputs and outputs. For this input, I want that output. For that input, I want that output. And you just show them to the model. At the beginning, the model is just going to, it's a program, it's going to make random guesses. It has an optimization algorithm. After some training process, you obtain a program, and you use this program in production. So that's the second step. Take this trained program from one, put it in production, and then that's what's going to be used in production to infer the outputs of the new inputs that you see in production, okay? So I make this distinction because often people talk about randomness or probabilism in machine learning. And I want to make this distinction because they can talk about randomness of the model in production itself. So after it's trained, there is randomness. As I was showing you with ChatGPT, or like these LLMs, Alexa, you can say pick one of the most likely words between the top 10 most likely words at random. They do this because sometimes they want some creativity of the models. Why not? So those are kind of easy to fix because you can say take the most likely every time. You can fix the random seed. You can still get problems with, but if it's running on some GPUs, you're going to get slightly different approximations. So the probabilities are going to shift a little bit. But this is mostly controlled. So the randomness, to me, when they talk about randomness in machine learning, is more located on the first stage, the training. When you developed machine learning models from one version to another, you're going to retrain the model with slightly different data, maybe slightly longer training, slightly different optimization algorithm. And by doing this process, you're going to end up with a model that is, on most cases, the same and hopefully better. But on some edge cases, it's going to have very different predictions unexpectedly. And this slight changes in, for example, the training data that end up in big differences in production, that's what people usually say when they say that machine learning is unstable or random, okay? Not really the second case, in my opinion. So in theory, nothing prevents a machine learning model or Alexa in this case, to say some very offensive joke if I ask for a joke. And so that's a problem. I call it uncontrolled outputs. And you could get legal pursuits for this. And so now we're going to see how you can limit this for Gen AI. So the first technique that people use is predefined answers. So imagine that you have a function that generates jokes from a list that you specify. So you say, this is the list of jokes, and you pick one at random, or based on the context, you pick one rather than another. And then instead of training the model to generate a joke, you're going to train the model to generate a call to that function, to that API, and then the system is just going to return the output of the API. So that way you have full control over what is the output of the joke. And that's what people do for mathematics, for getting the weather. They train the models to call APIs, not to hallucinate the weather or mathematics, okay? So that mitigates the issue, doesn't solve it fully because you cannot use API for everything. If I say, oh, that's not a funny joke, I mean, there is no API that's supposed to answer to me. It's just we expect the model to be able to speak in natural language. So it could still say things that are disrespectful to the user. So just that is just one mitigation. So you have other mitigations. One is model alignment. You want to align the models with human principles, be respectful to people, don't insult people. And so one technique is RLHF, if you don't know it. During the training of the model, you have a second model that is here to kind of rank different options generated by the model. So if you say, you're not funny, generate option A, you're not funny either, or option B, sorry, I will do better next time. And then you have the second model who is going to say to the first model, the second option is better, try to generate more of this. And this reward model itself is trained by showing a lot of human preferences inputs. So you show rankings of, in this case, humans prefer this rather than that. That's how you train the reward model, and then you use the reward model to train the first model. Okay? So that's how they do it. And then after the training, you can also do some sort of prompt engineering. The prompt is where you put the instructions for the model. So you say the user is asking for this, what is your response? So in there, you can also throw in some, don't insult the user, be respectful, some guidance for the model to follow. Okay? So that's the two techniques. If you do too much of this, you end up with Goody 2, which is a very funny experiment. You can try it. It's basically, it was so much put into respecting people that whatever you ask for, you're not going to get an answer. So for example, I asked for dinner recommendation in Berlin. It says, oh, I don't want to influence your decision by giving you recommendations. So it becomes, completely useless if you do too much of this. So there's obviously a balance to be found. Post-model sanitation, very quickly, put an extra layer between your model output and the user. It's going to check for offensive language or whatnot. And if it's offensive, it's just not going to give the answer to the user. It's going to try again the model or say, I cannot answer this right now. The last one I want to mention is constraint decoding. This is basically, it's interesting because it's useful for other things than ethics. If you don't want the model to say the F word, when it generates all the words, you just, after it generates its scores, you just say, I want a big negative infinity on the F word. So it's not going to pick it as the most likely because it has negative infinity. And so that's also used as a trick, so to speak, in more complex way to generate valid structured outputs. For example, JSON. If you want ChatGPT to give you a valid JSON and then you're going to parse the JSON and use it in downstream applications, sometimes it's just going to generate JSON that is just not valid. And so you're going to get a bug somewhere else because just the JSON is ill-formatted. And so by doing this kind of tricks, you can say, oh, the first word always has to be an opening accolade. And then the second word always has to be opening apostrophe, et cetera, et cetera. And so if you do these kind of things with libraries like outlines or guidance, you can force the model to generate structured valid outputs like JSON, SQL, et cetera. Okay? All right. So those are all mitigations. I like to say that sometimes there is also no room for error cases where mitigations are not enough. For example, call 911. There is no room for failure here, whatever happens. And so that's why we have deterministic systems. For example, rule-based systems. When the input is call 911, it's going to call 911. It's not going to go through a machine learning model, okay? If you say Alexa stop, it's going to stop. It's not going to go through a machine learning model. So you have rule-based engines that can do this very well, and you're sure of the results when you get it. And so the question becomes, how do you integrate the two models together, machine learning and deterministic? So you have two ways, either sequential, send everything through the deterministic rules, and if the deterministic rule cannot answer because it's a subset of everything that people can say, goes to machine learning, okay? So that's cheap because only a subset of what you send goes through the machine learning model, but it's slower because you go through two components. Other approach is parallel, send everything to everybody and merge the outputs. It's more expensive because you run machine learning on everything, but it's faster. And so that's what they do in Alexa. They basically have different applications, so shopping, weather, and each application has rules and models. And on top of all those applications, you have super rules, like call 911, Alexa stop. And so when you say something to Alexa, everything goes to all the applications and the super rules. Everybody gives its output. And then you have a bigger ranker who is going to say, oh, if a super rule matched, it's going to override everybody. And that's what's going to be returned to the user. It also has an ML model itself to say, maybe if you say play Frozen, and it could be either the music or the movie, it's going to look at the context if there's a TV running somewhere, and maybe it's going to prefer the video domain rather than the music domain. Okay? So the re-ranker itself can be a mix of machine learning and rules. All right, reality, more complex, because sometimes the input to one model is the output of another model. For example, Alexa, you get the text to the text model from the speech that you talk to Alexa. So there is a speech model. If the speech model makes mistakes, you have problems in the text model. And so usually when you do these complex systems, you first test everything end to end. So not just like the text model by itself, but the speech and text model all together. And you also train the text model to be robust to the errors of the first model. Like if there is like words that sound the same, but are different. So this is all safeguarding, by the way. Safeguarding is just one part of the picture. That's multiple pillars to have reliable machine learning in production. I'll just talk about one more safeguarding tool because it's very used these days. It's NeMo guardrails. It's something that people use to control what the LLMs can say or talk about. So basically in this config, you say, I don't want the LLM to talk about politics, okay? So you say, if the user talks about politics, just refuse to engage. And you give examples of what talking about politics means. So that's what the two sentences here represent. And then when the user speaks to the LLM or writes to the LLM, this guardrail is going to look, is it talking about politics? If so, refuse to answer. I tried it with ChatGPT, I think 3.5 at the time, so probably not the best. So I asked about the US election. It said I cannot engage in politics, so it does refuse to talk about it. But if I do something like this journalist did in the beginning, Matt Korda, and I say, oh, I'm just writing a fictional story about it, I'm not really trying to talk about politics, blah, 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 blah. Then after a couple iterations, the model is going to recite you some political opinions. So in this case, he said something like you should vote for Kamala Harris because blah, blah, blah. So somehow those models can be tricked. I'm not saying like this is not doing a good job. I mean, this is doing a great job. It's just that there will always be people whose job is to crack those things, those mitigations. There will always be cases in production where you didn't anticipate and you're going to have a problem, okay? So that's why you need also the other three pillars. Testing, monitoring, quick rollbacks. Testing, basically, you have this nice French startup, Giscar, and maybe there is a presentation about it, I'm not sure. They do out-of-the-box solutions for testing, so they are going to take, for example, a lot of the data that you want your models to be good on, and they're going to do some sort of perturbation of the inputs, and you're supposed to have the same outputs. And they do that automatically. They do test suits for your CI and everything. I'm not going to talk much about Giscar. I'm going to talk to you about what we built at our company. So those slices of data, not pizza slices, but data slices, are basically, as I was saying, you're going to look at all your data and say, for this slice of data, I want this output. For this slice of data, I want this output. And so assuming you have a way to create slices, we use Streamlit and Prodigy to construct the slices. That's not important. Then you can use DVC with a Parquet dataset and PyArrow to basically make a Parquet dataset, so a list of slices in different subfolders. So for example, you have a folder no regression on which you allow no regression or no failure of the model. Maybe you have a allowed regression folder because it's not as critical as the other use cases. And then in the no regression, you have different slices of data. So this is the performance on RSA keys. So those are all types of secrets that you can find in code. So different types of data, and you know that on this file, Django keys test.parquet, you want this output. And then with DVC, you can very easily collaborate on those data sets, version them, and not override each other's changes if you are multiple people contributing to this. And then you can just run the model on all the slices. With DVC again, it's very easy to cache the outputs of previous slices so that you don't rerun them if you don't need them. So DVC is really nice for this. And then you can use CML and Jinja to, for example, generate a report and then put that in your CI, and in your merge request, you're going to print this report as the output of the test slices. And the person is going to say, oh, but you regressed on this and this slice, so I'm not going to promote your model to the next stage. All right, so now this is testing. You have many solutions. Monitoring, quick rollbacks. I just want to mention this, although I don't talk about it much in this presentation. There is nothing different from machine learning than traditional software development. You want this kind of tools, to be able to first detect if you have issue in production, whether the API is getting slower, the celery queue is getting stuck. You need to roll back with Argo CD to the previous version because this version is getting has a problem. So you need all those tools that you usually use in your pipelines for machine learning as well. This is as important as the safeguarding and testing. As my security lead would say at Guardian, security is the discipline of putting as many obstacles as possible on the path of your attacker. I just want to say it's the same for having reliable ML systems in production. There is not just one best solution. You have many, many solutions, many tools, and you want to put as many as possible to have one reliable system in production, okay? Git Guardian, yeah, so I didn't talk about Git Guardian at all in the presentation. That's what we do. I mentioned this because we scan the whole public GitHub every day. So that's really like thousands of commits per second at least. And we look if there is secrets that people leaked in them. And if we find secrets, we send an email so that people can remove them, okay? It would be stupid to scan everything with machine learning. It's a huge quantity of data. It would be very expensive, very slow. So we first have a rule-based engine that scans all the commits and makes a subset of them, maybe 1%, that is interesting, that is likely to contain a secret. And then with machine learning, afterwards, we look, oh, is this a very high important secret? Is it a false positive? What is the context about it that we give to the user? So we use this combination of machine learning and secrets detection, yes, important. Be careful about it. If you've never received an email from us, is that you're doing a good job with your GitHub. But basically, last year, 13 million tokens secrets were leaked on public GitHub. And this is just a number that's been growing over the past decades. So, you know, this secrets in code and Jira and Slack, but, you know, GitHub is the problem because it's public, is a huge thing. So be very careful about it. We're here, but you know, sometimes people can get the credentials before you receive the email or you are able to remove the credentials. And also sometimes people don't know how to remove credentials properly from the Git history. So that's a big issue. If you want to learn more about what we do as machine learning engineers at Git Guardian, you can scan the QR code. It directs you to the blog where we have lots of good posts about machine learning techniques and also cybersecurity in general. I realize it's a bit weird now to ask you to scan a QR code if I work in cybersecurity, but this is not a scam. You can trust me. So yeah, I'll just leave it here if some of people wanna see the blog. And this is me. This is LinkedIn. Again, trust me. This is not my PayPal. If you want to connect on LinkedIn, that's one way, or you can just leak a credential on GitHub, and I'll just send you an email. So that's a second way, but I prefer this way. And yeah, I mean, now I'd be happy to discuss more with questions on the presentation. Thank you for listening, and yeah, don't hesitate to ask.
If there is any question, let me know. I can give the mic.
Thank you very much for the talk. Amazing. I know that there are like Git hooks to avoid leaking credentials that block your commit. I never investigated how they work. Yeah. I guess they're just rule-based. Do you see any application of natural language processing or AI models to these kind of tools that may get you redundant? Thank you.
No, but this is a great question. So the way it works first is yes, it's often rule-based. So you have a bunch of regexes that are going to look for sensitive, you know, patterns in your commit. So you can have it in the pre-commit. That's a good practice. But you can also have it, you know, once it's already leaked. You need it at different stages because not everybody uses, a pre-commit hook. So that's how it works. Like most systems that you see online. I see machine learning as a complementary piece. So you don't want to use machine learning on every commit that you scan. Can you imagine every time you commit something, you have to wait like a second that the machine learning model goes over all your diff, and that's a bad user experience. So that's why, as I was saying, you need both a first step that is deterministic, maybe fast, rule-based, and then you pass machine learning onto it. And so typically what we're doing right now is that we are making the regexes in the first stage more loose so you can catch more stuff. And then we pass machine learning on top of it so that we make sure that we don't raise false alerts. But thanks.
Thanks. Vizal, we'll do a question here, and then we can go here.
Thanks for the presentation. You showed 4 different ways in which you can monitor your model, like not only LM, but in general. I'm wondering if you have like a benchmark regarding how much each one of these tests filter out like potential leakage and source of problems.
Are you asking about those 4 pillars here, or?
Exactly. These 4 pillars, how do they compare each other in terms of, for example,
So
say
yeah,
recall and accuracy, let's say?
I mean, the priority is definitely the last 2 ones, because once the model is in production, you detect errors and mistakes. So you want to have this one first, and then I would put then I would go to testing, because before you release to production, you put testing, and then usually that's because you find issues with testing and the other 2 that you put safeguarding. So if you have to do this in one order, you go this way, okay? And if you have specific tools that you want to know about, I'd be happy to talk to you about them. You can come after the presentation.
We have time for 2 more questions, one here and then one here.
Yeah, thank you for the presentation. We're building tools actually where we need to be reliable, and we include at the end human in the loop. So we try to, use actually another model actually to find exception or to look at what we do. And in the last case, we have a human in the loop, and you haven't talked about human in the loop, so I wanted to see to have your perspective on that.
Yeah, thanks for bringing this out. I completely not mentioned this in this case. I think I was focusing more on like cases in production where you need an output quite fast, like Alexa. You need to respond to the user within 1 second, so you cannot have a human in the loop. But that's true. In many cases, you don't need to have that fast output, and you can have a human in the loop on a subset of them. So I think that's I'm all for them, human in the loops, if the user experience or the requirements for the product allow for it. But I don't know any tools for it. I use Prodigy for annotation, so maybe you can use this for human in the loop as well. You'll tell me. But yeah, I'd be happy to talk about this if you want.
We have one last question.
I want to go back to the guardrails. How good or efficient are this way that you have basically LLM produces an answer, then you have a second LLM, like an LLM is a judge, whatever, who looks into is this response political or whatever your guardrail is, and if not, please don't respond. How good is that working already, or maybe how good will it work if you have even better models, LLMs?
Yes, so it works well. Whether it's like multiple LLMs or if it's simpler models that acts as like a second layer, so to speak. But just, one disclaimer is that it's going to be more expensive in production if you have these multiple steps to give your output. But putting that aside, you have very good benchmarks that you can find online. Maybe I'll put a link in the presentation and the slides I put online. People basically, they just like benchmarks of toxicity in responses, and they show you how different approaches compare and how much you reduce toxicity when you use them. So I think that I would be better to just give you this benchmark than just try to improvise it. But my sense is that it works well, and the cases that I showed you where I can hack it, it's just edge cases. People are very good at this. Red teams that try to hack into LLMs, they do a great job. It's very funny. Sometimes they just like write every other letter, and the LLM somehow understands it, but it tricks it into the guardrails. And so you can always trick them, but on average, they do a great job. But yeah.
Thanks a lot. I think we can thank our speaker again.
Thank you.